The hidden Markov model, or HMM, is one of the most popular models to use for sequential or temporal data. And it might be so widely used because it's simple enough. So it works well because it's simple enough that you can actually estimate the parameters and you can efficiently do inference in an HMM. But it's also rich enough that it can handle real-world applications. So the HMM is sort of the go-to baseline model for sequential data. So what is an HMM? So in an HMM, we have some random variables, which I'll denote as Z1 through Zn, and these are discrete random variables in some finite set, and let's just number those from 1 to m. And so these are going to be the hidden variables. And then there are some other random variables, x1 through xn, the same number. And let's say that these take values in some set, capital script X here. And this could be discrete, it could be finite, or it could be, it could be real valued, it could be RD, and so on. E.g. And these random variables in the HMM respect the following graph. The joint distribution on these random variables respects the graph, and that doesn't disrespect, it respects the graph Z1, X1, Z2, X2, Z3, and so on, up to Zn, Xn, Xn. And this is sometimes called the trellis diagram. So this is sometimes called trellis diagram. This is the graphical model for an HMM, this here. And these x's, so the x's here are observed random variables. We observe some data. So that part of the setup here is that we have some data. Usually the setup is that we observe all of the x's. You wouldn't have to observe all the x's, but for now, let's say, you observe these x's. So this is like your data. And the z's, these are, so all the x's are the observed variables, and the z's are the hidden or latent variables. So this is the hidden part. Before, when we were talking about just a Markov chain or a Markov model, we just had the x's, and we had it looked more like this. If you didn't have all these x's here and you observed the z's, then this would be a Markov chain. This would be a Markov chain because it has this chain structure, and the z's are taking they're taking values in a countable set. So these are discrete random variables. And this is sort of discrete time. If you think of t as, or this subscript as time, you can think of this as a discrete time sort of process. 1, 2, time equals 1, time equals 2, and so on. And so, since these are observed, maybe following our earlier convention for graphical models, we could shade those in. So this is the model. This is the model, or the whole, the probabilistic model. And let's write down what this means. The fact that this respects, that the joint distribution respects this. That means that the probability of, it's the joint, it's on all of them, right? So we need, I guess I could do it that way. X1 up to Xn, Z1 up to Zn. The joint distribution on all of these random variables factors in the following way. Probability of Z1 times the probability of X1 given z1 times the product. So now we can just do all the rest of them in the same sort of way. K from 2 to n, k will be the index. The probability, so let's see, I did this one, I did this. Now I need this guy, so it's going to be the probability of zk given zk minus 1, and then the probability of xk given zk. And then that will go all the way up to n, and that describes the factorization. That is the factorization that this graphical model corresponds to. So this is the joint distribution. So whenever you think, it's usually helpful to think graphically, visually, to think of this. But this is what that means. And let me give you, actually, I wanted to show you a cool little thing. I think, I mean, so one of the applications of hidden Markov models is handwriting recognition. And I don't know if this particular, I have this little application for my pen tablet, and I thought it was so cool that, you know, and I think they probably use HMMs for this. But if they didn't, they could. I know that people do use HMMs for handwriting recognition. And so this little thing, it works so well. It's amazing. It's really cool. Hidden Markov model. Scratch. So anyway, I just wanted to show you that one little application of hidden Markov models. So in that little application, the handwritten digit, you know, the thing that I actually wrote down would be the observed thing. So like the first letter M in that Markov or H, I guess, in that would be what you observed, this X1, and then the latent thing would be the abstract thing. What letter of the alphabet? So this would be like 1 to 26, or I mean, if you want to have capitals and other stuff, you know, all the symbols that you might have written, and that would be the hidden thing. And then you go to, so then this next guy, the next letter, it's not going to really depend on the particular way that I wrote the H. It's going to depend on the fact that it wasn't H. So, you know, HIDDEN, etc. So what are the parameters of a hidden Markov model? So hopefully that little example sort of makes concrete how you might, you know, what this sort of abstract thing could look like in a real-world application. So in that abstract thing, the hidden state was the actual, the actual abstract letter or symbol, and the observed thing was the strokes of the letter, the handwritten thing. So what are the parameters for this type of model? This is actually sort of a class of models, and you can choose. You know, I didn't specify what all these distributions were. And so let's write down, or all these distributions were. So let's write down, let's make a little more specific. So the first set of parameters are what are called the transition probabilities. Transition probabilities. And these are, sometimes we write them as Tij. This is not completely standard, and sometimes people flip the I and the J here. But the transition, and let me actually write it this way, Tij. This is these probabilities here. So this is the probability that zk plus 1 equals some value, say j, given that zk equals some other value I. And I put I and j here because it's sort of the probability of going from I to j. So we could write this as, so that's just this right here. But I don't want to put I given j because this is just our shorthand where we sort of drop what random variables are equaling other things. So these are the transition probability, and this is, we have to choose these numbers for all I and j in our finite set from 1 to m. All the possible values that the hidden variables could take. And of course they have to satisfy the property that when you sum over sum over j, that it sums to 1 and they're non-negative and all that good stuff. And actually this T is you can form a matrix, an M by M matrix called the transition matrix. And that is a stochastic matrix. It's called a stochastic matrix because it satisfies those properties I mentioned. So that's the first set of parameters that we need to choose. The next set of parameters, or maybe a little even more general, is the emission probabilities. In order to specify an HMM, we need to choose emission probability, and let me use epsilon sub I of x. And this is, so epsilon for emission, the probability that for, this could be like a density. So I'll write it this way to indicate a density function. So if this were a density, it would look something like this. The density at the value, actually, I guess I should put just x here, not xk, given zk equals some value I. And this is for I in this set, and x in the set that the x's take values in. So in other words, this epsilon for each I, epsilon I is a probability distribution, say a density, on this space capital script X. So if it were a density, this, maybe we would write it like this. Or if it were if we wanted to have a discrete random variable, if we wanted the x's to be discrete random variables, then we could have something like this. You could also write it this way, but just to make it, concrete, this is the distribution for xk. Or it's going to be used for the distribution for xk. So this is probability that xk equals little x, given that zk equals I. PMF. So these epsilon i's are going to be used here for the probability of the x's given for the xk given the zk, and also here for a probability of x1 given z1. And there's one more set of parameters that we must choose. The initial distribution, right? So far we've done these guys, and these guys, and we just need to do this guy. So you need to choose an initial distribution. And this is just, let's just call it, since we're naming everything, let's call it pi of I. This is a convention. This is sort of a convention. People often use pi for the initial distribution. And that's the probability that z1 equals the value I. And this is, it has to be a PMF, of course, over the values 1 to m. So the joint distribution, if you plug all of these in, the joint distribution, maybe let's write it down. Let's write down the joint distribution. The joint distribution is the same thing. Let me just put x and z maybe. Now that's a little confusing. So it's x1 to xn, z1 to zn. Actually, I'm running out of time here. Let me stop there. We'll write out the joint distribution in terms of these parameters just to make everything completely, so that make sure you understand what these are saying. And then I'll give you just a little, maybe a couple little remarks about choosing these distributions or common choices for these distributions. Okay, see you soon.